Hi everyone, welcome back. Okay, so I did skip 2 slides if you're looking at the PowerPoint. That's simply because I kind of summed it up in my last video. Now let's jump straight into our equations of motion. So we know that a motion of particle is governed by Newton's second law, which is going to connect our unbalanced forces to its acceleration. So if we add all of our forces together and they don't sum to zero, we have a resultant force. And that is going to be proportional to the acceleration. The acceleration will be in the direction of that resultant force. So let's look at this right here. We have, two forces like this. Maybe I have an acceleration right there. But the way we get that is simply that, well, when I add these two forces together, they sum along this line. And guess what? My resultant force is along the same line as that acceleration vector right there. Now, there are always a bunch of ways to do these problems. And if you like doing things with the vector summation method, like doing it graphically, this is a great way to do it. But you can also just always break things into components, and then your acceleration will have components as well. You'll have the AX component, and the AY component, and the AZ component. So you can do this as vectors. You can also do it as like 3 sets of equations for the scalar components of your vector. But you just do what works best for you, okay? Do what works best for you. Now, our equation of motion is only valid if we're in a Newtonian or inertial frame of reference, okay? But what in the world does that mean? Well, we have motions that are concerned with things that are near the Earth's surface. We typically assume our inertial frame is fixed to the Earth. We're just neglecting the fact that the Earth is rotating, and so therefore everything's kind of rotating with it. Okay, the surface of the Earth doesn't move. Now, for problems that are involving satellites or rockets, we have to fix it to the stars. And I hope you're noticing the word fixed here. Okay? For an inertial frame of reference, we need to have a fixed frame of reference when we're looking at things. That can change at various times in the problem, depending on what we're doing, but we have to have a fixed frame of reference. We can't just move along with it. So I'll keep on going. Now, what do we do if we have a system of particles? Okay, this could be a gas. And notice we have an inertial coordinate system, so everything is measured from a particular point in space. Now, in statics, there are internal and external forces acting on a system. All these balls, they bump into each other. Bump, bump, bump. However, do you remember what the difference between those two was? Like what an internal and an external force? Which one actually mattered? Okay? Well, the internal forces do not matter for these systems. Just like with statics, internal forces are all equal and opposite in direction, and so they all sum to zero. So only our external forces actually matter. But what about the mass? What about the acceleration? How do we tell what's actually moving? Am I looking at each individual particle all at once? You're not. You don't look at each individual particle. What you do is you say that, okay, at any particular point in time, the center of mass, which is this point where if I were to have a weighted average of all their positions and their masses, and I have it right here, think of it as like the point where I balance a seesaw. If I've got a lot of mass over here and a little bit of mass over here, then the center to balance is going to be over here. It's very similar. Just think about it in 3 dimensions now. You're trying to balance everything with all the different masses pulling on you. So what we assume that our forces are applied to is this center of mass. And then therefore, this leads to an acceleration of our center of mass. And if we want to, we can then connect that right back to our particles, where all of them are going to have the same acceleration. Okay, so let's sum up some things here. I'm going to pull these all up here. And yes. So first off, Newton's second law is a law of nature. It's experimentally proven, not some sort of magical analytical proof, which means that there are certain cases where it doesn't work. like when you get to really, really small objects or really, really high speeds. Mass is a property of an object, and it's the resistance to a change in velocity. And pound force is not mass. Don't make that mistake. Weight depends on our local gravitational field. It means it's going to change when we're on a different planet. You have a different weight on Jupiter or the moon. And that's because it's proportional to gravity. Mass does not change, your weight will change. Finally, unbalanced forces will cause the acceleration of objects. And this is our fundamental to all of our dynamics problems. We've been doing dynamics this entire time, we have, but we're really doing dynamics now. Okay, so I think I'll stop right here, kind of sum it up, and next one we'll go over a procedure to solve these problems and jump into an example. So thanks for listening, and I'll see you all next time.